We are on slide 33, by the way, after this. Okay, Richard, all to you.
Okay, I'll go forward to slide 33.
Yeah, basically part 3 of the presentation.
Well, I think we finished it. I'll move it forward actually to 34.
Yeah.
So this is Hisham 1's irradiated fuel disposal facility, very different to Hisham 2. This is a glass window, a bulletproof glass window that's filled with a solution called zinc bromide, which gives you radiation protection. In essence, it's a similar arrangement in there's a dismantling tube where you pick things up and put them into various holes. So around here, this is the equivalent to in Hisham where there's a dismantling facility in the middle, but you pick things up, and this assembly here rotates around and lines it with these holes, and you can lower the assemblies, the parts of the assemblies into the various holes, either to the pond or to the debris vault. You'll notice here how clean this is, because this is done by a man using manipulators. So as Hisham 1's using electrically powered tools, a lot of the work in here is done using manipulators. So and because they can see what they're doing, so they have a vacuum cleaner in here and they clean it up all the time, keep it nice and clean, which isn't possible at Hisham 2, but it was at Hisham 1.
Yeah. Information to this. I think from my memory, this is about the opening aperture that you're looking through is about 600 millimeters or 60 centimeters or so. Is it bigger?
Probably about a meter. Yeah, it's quite a big window, and that's part of the problem. So the reason why there's no big window at Hisham 2 is this is it's bulletproof glass. It's not earthquake-proof glass. So in a seismic event, it would be possible that this glass could break. So again, time of risk argument for Hisham 1 gives you the nuclear safety case. Often you have an assembly in there. It's likely to be an earthquake. So that's how it's done.
Yeah.
So Hisham 1 also, funny enough, this area here behind the glass is CO2 pressure, whereas Hisham 2's irradiated fuel disposal facility is in air, atmospheric pressure. This is in pressurized CO2, and can actually take an assembly direct from the reactor after it's been taken out and could dismantle it because it can deal with 100 kilowatts, whereas Hisham 2 irradiated fuel disposal facility can only operate at 10 kilowatts of decay heat in the assembly. So it wasn't all advancement between Hisham 1 and Hisham 2. There were some bits where things weren't quite as good for all sorts of reasons. This is a very simple disposal cell. Again, everything's Hisham 1 as simple as I said earlier on, but you can actually see what you're doing. But the Hisham 2 was the seismic safety case, which actually
Richard, you're quiet. Richard, are you on mute?
After we've taken the assembly out of the decay store, there was an error on the slide there. Point was additional cooling of fuel elements for a minimum of another 40 days. It's a total of 100 days decay between taking out the reactor, 60 days in the decay store, another 40 days in the cooling ponds. I can see why that error has been made there. And it sits in the pond to further move decay heat from the fuel. We have a skip. We'll see a picture of a skip later on that can contain up to 15 irradiated fuel elements. The water in the pond is 6 meters deep, gives shielding, so you can actually see the elements sitting in the pond, and you can have a look at it because it's just below the water. The water is further dosed with boric acid, although it's irradiated fuel and depleted. We do dose it with boric acid to give additional criticality safety. And then we balance it up with a bit of sodium hydroxide to keep the pH at 7. The water is continually cooled and filtered to remove any insoluble matter and particular matter because of potential items floating on the surface giving a radiation hazard. So in the pond, do you want to do the Helium 2 pond, Connor?
Yeah, sure. I can do the main features. So effectively what you've got here, remember Richard talked about the fuel being received from the IFD, comes down a chute into the element reception tube, which Richard's got his pointer on there, and that's got a shock absorber in it. So the fuel will come down, each element will come down, received into that shock absorber. It upends into a vertical position, and the pond crane, that yellow assembly, has on it what we call an element mast. So it's a grab that can pick up single elements at a time. It locates over the element reception tube and then picks up the single element and loads it into a skip, which will be in the loading position. And we the skips take 15 elements, and we load the stringer as it comes down into the relevant skips. So yeah, 8 elements per stringer and 15 elements per skip. Why is it not 16? Good question. Richard, do you know the answer to that one? I think it was original design size of what you can get in the flask.
Yeah, the flask size and it constrains you with 15.
Yeah, so we end up now with fuel that goes into the skips and stored in the ponds. As you can see here on the Hisham 2 design, you've got 2 pond bays, a number of skip locations there. At Hisham 2, we can store up to 45 skips in our ponds with 15 element compartments in each. So I'll do a quick math on that, but it's up about 680 or 90 elements we can store in the ponds at any given time. We typically try and manage that down to at the minute we're running quite low. Just incidentally, we've got it down to about 20% in the ponds, which is good. Other main elements then, so you've got the transfer area. So as part of that crane assembly, the yellow assembly, which has the element hoist on it, we also can pick up skips. So we have the skip mast, which picks up the skips, moves it over to the transfer assembly, and you see here then you load it onto a transfer trolley, which runs between the ponds and the flasking area of the plant. So you'll take a full skip full of fuel, land it into that transfer trolley, then it runs across in the skip transfer trolley into the flask handling facility. Other bits you've got there, you've got the control room just to the right hand side, so the operators will receive the fuel from the AFD on one console, and then to transfer it through into the ponds in another console. They've got lots of cameras, other CI and indications to give them confidence that the fuel's been adequately received and managed. And there's a picture of the ponds, which shows you the 2 sides of the pond base, and you can see there you've got the skip transfer. Sorry, not skip transfer. The skip handling hoist submerged under the water. Our features have you got there? You just see the rails that it runs on. You've got the central island in the middle. You've got stop gates at the bottom there, which you can theoretically isolate each pond and drain down the area out with where the skip transfer trolley is. From memory, well, I know we certainly haven't deployed those stop gates in my tenure. I don't know, Richard, have you ever had to use them?
No safety case.
There you go. That's why we won't use them, because we haven't got the safety case to do that. So the pond, you can see it gives off quite a. It's pretty clean in Hisham 2. When you look at the bottom, you'll see the graphite deposits, etc. But the pond water itself is kept pretty clean. We have a weir system which bleeds the water out and recirculates it through filters and conditioning plant.
So it's just Hisham 1's pond. So like most things at Hisham 1, it's a lot smaller. And in fact, it's all boxed in, because one of the original design constraints of Hisham 1 after it started construction was a thing called spalled oxide. They were concerned about getting spalling of oxide from the stainless steel pins, stainless steel being undergoing oxidation in the CO2 environment. So they built it all in a big box. Well, they built it and then they put a big box around it to contain all the spore oxide, and then found when they run the reactor that spore oxide never appeared. So all the spore oxide modifications were a waste of money. So it's funny, isn't it? So the people model it all and come up with these designs, and actually when you run it in real life, it's not as you expect, which is very strange because you rely on people to design things and design them right. But when they did the modeling for what needs to happen, it was wrong. So Hisham 1, a tiny little thing again, as you can see here, to actually pick up stuff. And here's the first picture of a skip in this murky water. Hisham 1 suffers with algae growth in the pond, and they've come up with all sorts of mechanisms trying to get UV filters to try and kill the algae as it's whizzing around in various tubes and things. Not been particularly successful. So there is, it sounds awful, doesn't it? A nuclear power station, a bit of algae growth, but it's all safe. It just looks a bit murky when looking in the water. So this is the grab that can pick up an individual element. You see the elements just very dimly in the water there. This grab can pick up an individual element, and this grab here can pick up a full skip and move them around. So you would pick up an element from the reception tube, as Connor said, pop it in the lower it very carefully, I should say, into the skip, and then pick up the skip with the skip handling machine and move it into the Hisham 1 different. There's no transfer trolley; it goes straight into the flask, as we'll see in a moment. So here's a picture of looking down on the 15 elements in a skip. I once had a bunch of visitors from the Ukraine who we took them into the ponds, and through an interpreter, they asked if could we turn all the lights off in the pond so we could see the Cherenkov radiation from the fuel. I presume you all know what Cherenkov radiation is, the effect of radiation passing through a medium where it's going slower than the speed of light. So we turned off all the lights in the ponds, which I have to say I'll never do that again because it was quite scary. And you can just see the Cherenkov radiation emanating from the fuel elements because of the radiation coming off them. So the blue, I have to say that blue you see isn't Cherenkov radiation, if people are thinking that. It's very, very dim from the radiation fuel element, but you can just see it if you turn the lights off. The blue is just the blue water, like in a swimming pool. Nothing to do with Cherenkov radiation. Sorry for disappointing anybody there. So.
If you ever get a chance to go to Silo B, whenever they take fuel out, you can see it with the lights on. You can see the Cherenkov radiation with the lights on. It's slightly green hue just beside the fuel. It seems, I don't know why, but the design of the PWR fuel seems to give it off a lot more readily. It's very interesting. Yeah, it's a lot more stood out on the PWR pond than the AGR. Okay, so this final stage of the fuel on site for the AGR is flask handling. So we've got two modes of operation between Hisham 1 and Hisham 2. Hisham 2 is a dry load site, and Hisham 1's a wet load site. We'll take you through that. Should some aspects of the design of a flask, and I mean largely the main flask process is very similar. How we get the flask on and off site for Hisham 1, Hisham 2. Yeah, number of key safety features and quite a robust design, I'd say. Richard, if you want to run on, that's.
Yeah, so Hisham 2 of the dry loading, where the flask is loaded by taking the skip out of the pond and putting the skip into the flask. Hisham 1 put the, as in with previous AGRs, put the flask into the pond and put the skip into the flask underwater, so it doesn't come out. The problem with that was envisaged at Hisham 2 was if you drop the flask, which weighs over 55 tons, if you drop it into the pond, you could crack the pond. And then if you empty the pond out, it's a bad day at the office, a really bad day at the office. The dose rates. So the Hisham power station is near the coast, and there's a public walkway along the coast. If you drain the pond inadvertently, although the pond is inside the power station. The dose rates at the site fence where there's a public walkway would be enough to give you a lethal dose in about 5 minutes. And that's through concrete walls and everything. So the water in the pond is extremely effective at shielding. If the water isn't there, it's not good. So how do we manage to operate Hesium 1 in a similar way? Well, again, it's time at risk argument. And also, actually, the pond is further away from the site fence as it happens, so the dose rates are lowered. So we take the flask, we put the lid on it. It's bolted down, is surveyed for any contamination, and then dispatched by rail. It goes all the way on rail from Hesium 2 and Hesium 1. Some of the other AGRs used to have a transporter. Thomas as a transporter. That's a sister station for Hesium 2 in Scotland. So transporters to take it from the power station to what's called the railhead. But Hesium 2 and Hesium 1, it goes straight onto the train and then it's sent to Sellafield. And we have some pictures to show you. So there's the diagram of the Mark II. We're going to see a video later on the Mark I. And although in the video it says that they were happy with how the Mark I performed, they still went ahead and made a Mark II. So you'll see the video. The video showed the lid moving slightly when it was drop tested, and they decided to redesign it with a lid that fits inside, and so it won't get deflected when it got dropped anywhere. So there's the flask body, which is a single forging.
Maybe worth explaining the fins on the side, Richard.
Yeah, sure. So it's a single forging. So you get one piece of metal, heat it up, and bash a big hole in the middle, and it gives you the flask. When we put 15 elements inside, we're allowed to have a decay heat of 10 kilowatts. So if you imagine you had 10 1 kilowatt fan heaters from your student rooms and put them inside, eventually the body of the flask does get hot. 10 kilowatts in an enclosed area does get hot. And if you touch the outside of a flask, it is warm, with the nuclear fuel inside when the lid's on and bolted down, and they're just cooling fins to remove the heat when the fuel is inside, because you can't turn the heat off. That's the thing about nuclear fuel. If you had 10 1 kilowatt fan heaters inside, you could switch them off and the thing would cool down. The decay heat just keeps going. And that's why nuclear is special. That's what we say on the power station. And so you have to get rid of the heat. So the fins are welded on, and they're not part of the original forging. They're welded on to dissipate the heat from the 10 kilowatts inside the flask. So is there any radiation coming off the flask? A small amount. We can talk about it in a bit about that. It's a single forging, as I said. The wall is 340 millimeters of steel. It's quite a monstrous forging. I don't think we've probably got the capability in the UK to make anything like that anymore. We have to look to Korea for big forgings like that, I would think. But there are a lot of flasks the company has. I'm not sure anymore, Connor. How many flasks does the company have?
About 30 in circulation for the AGRs, but this is where Java talked about how we're changing operations. So we're now, as an AGR fleet, moving to defuel what we call the Region 1 sites. So the first sites to start defueling will be Hinkley Point B and Hunterston, and they have announced defueling dates for the back end of this year and early next year. So what's that mean for us? That means that the amount of flasks in service between us and Sellafield will be we need to increase those to ensure that we can adequately manage defueling the operating sites, as well as expediting fuel being removed from the shutdown sites. As you can imagine, the hotel costs for operating a site which is shut down and defueling are quite extensive. So the priority is to get the fuel out safely, but as quickly as possible. So flash traffic, typically on an operating site, you can survive on 1 flask every week. That will be more than enough to satisfy the requirements of the site. But on a defueling site, you want to ramp up to, if you can, roughly 5 flasks per week. which means that the finite number of flasks in service becomes a problem for us. So at Hisham 2, we had about a dozen flasks that were original build, sat on our strategic stores from back in the 80s. We've just 6 months ago had them removed from site and taken to manufacturers for refurbishment and bringing up to standards for bringing back into service. So the number of flasks in service will increase by about a dozen above the 30 that we currently have to help mitigate the increased requirements of flasks for defueling and continued operation of the other sites. Sorry, you asked.
Okay, so the weight of a flask is when it's full is 53.3 tons. It says there. So we pick them up with what's called a 55-ton crane. We're very boring how we name things, so it's a very boring name. So there's the 55-ton manipulator which picks up the flask. There is it's actually lowering that onto the bogie at the moment. The train. You can just see the bottom of the train here. And when it goes onto the train, it has a cover, a hood pushed over it. So you never see these out on the train. If you're any train spotters in the room, you won't see a flask. You see the cover on the outside. Just as sort of a side, we have actually tested firing missiles at these because of the increased terrorist threat. And I'm pleased to say it was flask 1, missile nil. The flask is so robust that the missile failed to penetrate the thickness of the steel. Which is a later test. We did all sorts of tests before the days of terrorism, but now we do test them and they do survive a missile attack. So here's looking down on top. So you can see now that the lid, this arrangement here, is now inside the body of the flask. So although on the video we're going to see shortly, just say that the lid moving a bit wasn't a problem, they did redesign it. Actually, it was when I started with the company and designed it with the lid sitting inside. And all these bits here that stick out are all shock absorbers. They deform. And a bit like for those who are interested in cars, you have like crumple zones in cars where you have little bits that deform and reduce the energy of the impact. So these bits here are designed to deform and reduce the energy of the impact. Interesting little design feature here. So although there are bolts around holding the lid in, the lid is actually held in by wedges, chocks, like cheese-shaped. They've got little handles on them, and there's a double wedge arrangement. Very clever design that it doesn't rely on the bolt holding the lid on. It relies on these wedges that are put in. And obviously, the more if you have a door wedge, it's harder to try and pull the lid off with a wedge in. The more it digs in and won't come off. Very clever design. And the bolts are really just to compress the seal that keeps the fluid inside the flask. Very, very clever to reduce the reliance on an operator torquing down the bolts to the right torque value. That's not part of the integrity claim on the. Well, it's part of the integrity claim, so it keeps the fluid in, but in terms of keeping the lid on, it's kept on by chocks. So here we are with the full display of what's going on. So we talked about Hisham 2 being a dry loading facility. So this part here, where I've got the mouse, is actually in the pond water, and the skip is lifted out into the air and is rotated around and lowered into the flask, and the lid is then put on the flask. The flask is then taken out on a bogie, a transfer trolley, where the lid is bolted on, and then the flask is picked up and put on the so-called inspection stand, where it's cleaned and monitored for contamination and radiation. Do you want to take over, Connor?
Yeah, we also pressure tested there at that point. So we'll carry out a leak test on the seals to ensure that it's pressure tight. Like Richard said, we'll do radiological surveys as we move, and as the other sites move to defueling. That bay there, number 3, is quite important to us. So because you have the ability to carry out survey plus pressure test, etc. So where Richard's highlighting over the right-hand side now, we're developing a very similar capability there. So you've got multiple points where you can bring in several flasks to site and have them at any stage of the preparation and for either loading or deloading. at any time. So you increase your capacity to carry out flask operations. The 55-ton manipulators, the item that's on highlighted number 2 there. So that effectively becomes a lot more busier when you move to defueling. So our maintenance strategy and operational strategy for that becomes fairly critical. So we're installing a lot more condition-based monitoring equipment on that plant and buying in a lot more strategic spares, as you'd expect, to match the change in operational strategy. But effectively, to follow the process through, you pressure test it, confirm all okay at point 3, survey it, outgoing survey from a radiological perspective, prepare all your paperwork for dispatch, because now you're subject to RAM transport regulations, get all that signed up, and we become the consigner of the fuel offsite to Sellafield. It's loaded to point 1, which Richard showed the picture of with the canopy. Effectively, there's a hole in not a hole, a door, a hatch, yeah, a door or a hatch that opens up from the flask handling facility onto the railhead, and the flask is loaded onto the train line, which at Heysham 2 we run round then to Heysham 1 to a common railhead, and they're taken off. So Heysham 1 and Heysham 2 at the moment work together in terms of dispatch of flasks from that railhead.
Okay, so Heysham 1, very different again. So as we said, the flask is loaded with the skip underwater, so they can see the flask in the water, and the skip is put in underwater, and the lid is put on underwater, and the whole assembly is lifted out of the water and pressure tested, bolted up and pressure tested out of the water at Heysham 1.
And there you have it. That's a flask prepared to now go via DRS service. The logo, the little white logo, that looks like an old picture. We've got a diesel locomotive that we rent, which trundles between each site between Heysham 2 and Heysham 1. I think that's an original picture. Richard, is that right?
It certainly is.
That looks like an older version. But effectively, we run the carriages through, and then it's dispatched off to Sellafield for us. So the design of Flask, yeah, we've got an interesting video. If you want to bring it up, Richard, we can run through the testing that was done between the Mark 1 and the Mark 2 Flask, part of the development of the safety case for that plant. So this is showing you a flask that's now held on the train line. They run a logo into it.
So this is the Mark 1 flask where the lid's on the top. I'll just skip it forward a bit. So here's the forging. That's how the flasks are still made to this day. Check out the 1980s technology.
Yeah, look at that.
So we just move on to what we used to do with them. So we drop them. So this either models or real ones.
This
is far more onerous than crashing a train into it, I have to say.
Was this drop test on the Mark 1 Flask which revealed an issue?
Flask, yeah.
Yeah. There you go. So yeah, the way the lid was sealed, the arrangement would give rise to a slight pressure reduction inside the flask. Isn't that right?
That's right. Yeah. So that's why that's why the company went and designed the Mark II flask, which didn't have a train crash into it. But to be honest, the train crash was more about PR. It's dropping them the deceleration when they dropped it onto what's called an unyielding object, is the terminology in the safety case. The deceleration when the flask hits the ground is dropped from 30 meters high. The deceleration is 1200 G. So if you're in a car that's diesel at 200 degrees, then your brains will be all over your front of your face. So 1200 G, and that's the real test. The hitting with a train is like, oh well. To be honest, the 1200 G is the real test of the flask, and this drop test is the thing it's all about. So a lot of this is about complying with IAEA standards in terms of packages for dangerous goods. Drop tests are required in terms of the IAEA transport regulations, and that's what this is about, really. So we'll just skip forward again to setting the train up. It's quite good.
You guys got to be aware now. There's some really modern computers in this video. Don't get jealous.
This is the British Rail test. Well, British Rail at the time test track.
It would have been incredibly fun to do that. We don't get to do anything like that nowadays.
So I have to say I disagree with that, because it wasn't a tremendous test. What it was about was a bit of PR, really, because I think people worried about having flasks on trains, and the real test of the strength is let's be honest, it's dropping it onto an unyielding object from 30 meters high, and the deceleration is 500 feet. By the time that train hit it, it tickled it, really. So the train disintegrated and lost some of the energy as it hit it until the engine block hit it. And the engine block, this is an old-fashioned big diesel with a big diesel engine, but the engine block would have caused the damage. But of course, it lost all the energy as the train crumpled, like in a car. So the real test is the dropping it onto the yielding object. But it's a good bit of PR.
That flask is currently resident outside the N02 skills centre, and if you look at it, you've just got a couple of fins which are slight bend in them, and that's it.
Okay, our time is done.
Well, thank you very much, everybody, for your efforts and your patience. This is going to be in 3 parts. Although in the timetable I've allocated 2 lots of 45 minutes, what I will do, obviously, I will make sure that you guys get extra time to basically watch this again. And for those of you who are on the distance study, you shouldn't make any difference. You just watch as much as you want and then come back and continue where you left off. And often we encourage you to really go back and listen to the recorded material again, just in case you missed something. So we'll bring this to an end. I'd like to thank Richard and Connor for their efforts. I know they were both very busy, and we appreciate the collaboration of the EDF with our academic support. And we would also, obviously, if need be, reciprocate our efforts in offering similar things to EDF. Well, with that on board, I'm going to stop recording this. Thanks both for your support. Do you want to say anything before you leave? Richard?
I suppose I would say that I had 30 odd years in the nuclear industry and I loved it. I might have been at one place, but I did love the job. It's a great job. I really enjoyed it. And we worked all the way from conventional side onto the fuel route side, and I think I never had a dull day.
And the other thing I would add to that, Richard, is the having worked in both Issue 1 and Issue 2 and UK at large, within the United Kingdom, we've got the best and safest nuclear power stations.
Oh, yes.
So the reliability and the amount of effort goes into making sure that they're safe, they're safeguarded, and they are secure. And that's the most important part. So thanks again, all of you. Connor, do you want to say anything?
No, just thanks for the opportunity again, Javad. I really enjoy coming and talking about the fuel route. But you're right, Richard, the industry is ever changing, and you have a look at the developments around the UK at the moment in terms of Hinkley Point C and Sizewell C to come. The opportunities are vast in the nuclear industry. And as we move into decommissioning and defueling of the older sites, again, there's lots of work and lots of fresh blood required.
Excellent. Thank you very much. I'll stop this recording and thanks for coming.